All right, are you able to see my slides?
Yes. So
Great.
Conrad will tell us about two mechanizations of WebAssembly 1.0, and the floor is yours, Conrad.
Great. So, hi, yes, I'm Conrad Watt, and I am going to be talking about our paper, Two Mechanisations of WebAssembly 1.0. And this work was carried out in collaboration with Xiaozhe Rao, Jean Faribault, Martin Baudin, and Philippa Gardner. So, excuse me. Perfect. So first, let me introduce WebAssembly, sometimes shortened to WASM. WebAssembly is a new bytecode language supported by all major web browsers, the first language to have wide native support on the web since JavaScript. It was originally designed as a compilation target for low-level languages without garbage collection, such as C, C++, and Rust. And excitingly for us, WebAssembly's official standard specifies the language by way of a formal semantics. This is quite unusual for an industry language. To give a little more context on the timeline of previous work here, the original draft pen and paper formal semantics of WebAssembly was circulated around late 2016 to 2017, and later published in PLDI 2017 by Haas et al. Work was carried out on mechanizing this semantics in Isabelle Hall by Watt. A number of errors were discovered in the pen and paper draft, which were fixed before its publication in PLDI. A separate paper in CPP 2018 was published detailing the mechanization. But then after all of this, the W3C Web Standards Organization published the first official release of WebAssembly's formal semantics in late 2019, which contained some changes and extensions. So I'm presenting the following results today. First, WASM Cert Isabelle, an update and extension to the 2018 mechanization, which covers the refactorings and additions made by the 2019 W3C spec. In addition, in particular, I'm going to be talking about our new mechanization of instantiation. Instantiation is a linking and allocation phase of WebAssembly, which takes place before regular execution, and was not formalized by either the PLDI 2017 work on pen and paper or the CPP 2018 work in Isabelle. Finally, I'm going to talk about WASM Cert Coq, our new mechanization of WebAssembly in Coq. So this is a mechanization of the W3C 2019 semantics, which replicates all the proofs from the original Watt 2018 work, and we're continuing to extend it further, as I detail later. So to get more of an intuition regarding these models, I'm going to talk about WebAssembly structure in a bit more detail. WebAssembly is a stack-based language like the JVM bytecode, and most operations do not act on variables, therefore, but instead push and pop primitive values to and from a value stack. WebAssembly's formal semantics is specified by way of a small step reduction relation. Again, like the JVM, WebAssembly programs must be validated to obey a static type system before they can be executed. This type system ensures, among other things, that an operation only pops values from the stack if a sufficient number and type are statically guaranteed to be present at that program point, i.e. there are no stack underflows. WebAssembly currently has no first-class function references or any kind of structured type at the value level. All WebAssembly values on the stack belong to one of the four types listed on the slide. I32 and I64 are 32 and 64-bit ints, and F32 and F64 are 32 and 64-bit floats. This slide shows the execution of a very simple WebAssembly program fragment, according to formal semantics. The program fragment is written in the WebAssembly text format, an official human-readable format for describing WebAssembly bytecode. On the left column, we can see three type-annotated const instructions, which each push a single value onto the stack. The two add instructions each pop two values from the stack of the appropriate type and push back the result. Note that the value stack is not represented explicitly. Instead, the WebAssembly semantics treats the leading list of const instructions as representing the stack. In the first step of reduction, we see these two const instructions are popped from the stack as the first add executes, with the result 3 being pushed back onto the stack. Just to point out, if the program fragment were to attempt to push a float onto the stack, which would then be popped by an integer add, this is a validation error, and the program would not be allowed to execute. So now that I've briefly introduced WebAssembly code fragments, I can talk about the module. A module is WebAssembly's unit of compilation. It holds declarations of global state, which code can access, and also declares a list of functions which contain the program's code. Each function is type annotated, and one of the main behaviors of the validation pass is to check that the body of each function respects its type annotation. For example, the function shown on screen now is annotated with a type which indicates that it accepts a single I64 argument and produces an I64 result. In the body of the function, we retrieve the argument, add 400 to it, and return the result. So this would pass validation. The first kind of global state declarable by a module is the memory. Programs can store and load values to and from a module's memory, which is defined as a simple zero initialized linear buffer of bytes. The memory.grow instruction allows the buffer's size to be grown, while the memory.size instruction allows the current size of the buffer to be checked. Loads and stores which fall beyond the buffer's length immediately terminate the program with a runtime error. The table is used to hold function references and implement indirect calls or dynamic dispatch. For the sake of time, I won't go into the details here, but they're available in the paper. Finally, we have global variables. These are declared as a module scoped list accessed through static indexes. The global.get and global.set instructions shown here access the kth declared global in this list. Beyond the declared global state, a module may declare imports and exports. A module may import another module's exported memory or table instead of declaring its own. There is still a limit that overall a module may only have one memory and one table, whether imported or declared itself. There are other details of WebAssembly semantics, which I don't have time to introduce here. In particular, WebAssembly's control flow is quite unusual for a bytecode language, as it does not have arbitrary goto, but instead uses blocks, loops, and a break expression. Details can be found either in the paper or in the official formulas. And now that I've introduced the base definitions of WebAssembly's globally declared state, I can talk about the formal semantics. First, I'll sketch how it appeared in the draft. The two main components are the global store, which holds information shared between all executing modules, and the module local instance, which tracks the parts of the store that are in scope for the current module, along with some other module local state. Note that all of the instances currently running in the program are held as a field of the store in the left-hand side. So WebAssembly's execution, as previously noted, is defined by way of a small step reduction relation. The full reduction relation in the draft was defined between configurations, where each configuration is made up of three components: a store S, which we've seen already, a list of values, V star, representing the values of function local variables, and E star, the list of expressions currently under execution. The reduction relation is parameterized by an integer index k, which indexes the instance field of the store to denote that code is executing in the module associated with the kth instance. So the Isabelle Hall mechanization of WOT 2018 mechanized this relation along with the type system and carried out a standard proof of syntactic type soundness. It's also incorporated a verified executable interpreter and type checker. The mechanization was limited in that it did not directly model WebAssembly's underlying numeric operations, particularly those to do with floating point calculations, instead leaving them as uninterpreted functions, which are filled in with unverified OCaml when extracting executable definitions. It also did not cover parsing WebAssembly's concrete syntax or the instantiation phase, which, as mentioned previously, was not formalized by the 2017 draft. Finally, the mechanization dated quickly due to certain changes in the 2019 spec. So just to go back to the formalization of the global store and instance in the draft semantics, I'm going to use this to highlight some of the changes that were made in the 2019 semantics. So in terms of semantic changes, the 2019 spec extended the language to also allow globals and functions to be imported and exported, not just memories and tables. And in addition, as a purely editorial change, a new formal construct called the frame was introduced to hold the instance. So this resulted in these changes to the formal objects in the spec. you can see that the function and the globals, you can see that the list of declared functions in the program and the globals are now held in the program-wide store instead of being part of the instance, because now you can have multiple modules which share access to the same globals and functions. And the per module instance now has an indirection into the store in the same way that it did for tables and memories before. And as I said before, the instances are now tracked in the per function frame instead of being part of the store. So this is just a bunch of shifting around of different definitions, some semantic extensions, but also just a lot of refactorings, which keep the semantic behavior overall the same. And again, the top level reduction relation now uses a frame to hold the local variables instead of a direct list of values. So as I mentioned, part of the work I'm presenting today is in updating the 2018 Isabelle Hall mechanization. And this work was carried out incrementally on and off over roughly a year following the official 2019 standards release. So because there were so many editorial changes where definitions were shifted around, quite a lot of the existing mechanization had to be touched. Roughly half the lines of the code had to be changed, although most changes to the existing proofs, which referred to the revised definitions, were fairly formulaic changes. Getting a second pass over the proofs allowed us to improve on several needlessly lengthy proofs in the original model. So despite several large additions to the model, including the definition of instantiation, which I'll talk about shortly, the line count overall actually remains basically the same. So let's talk about instantiation, which is one of the biggest extensions to the model now. This is a phase, as I said before, where the definitions of the module are allocated in the global store and imports are satisfied. It's one of the largest single definitions in the WebAssembly specification. I've included a screen grab of the top level definition from the official spec for flavor, but I don't really expect it to be readable, especially since I haven't expanded any of the auxiliary definitions. So the most interesting thing for us in terms of the mechanization is that the definition of instantiation has a very weird quirk that I'd like to illustrate. It's actually deliberately circular. So to boil things down to their essentials and cut away the extraneous parts, the core of the instantiation definition takes as arguments the current global store S, a module to instantiate, i.e. we're going to be adding the definitions of this module into S as allocated objects. And finally, a list of imports to satisfy the import statements of the module. And the result of this is an updated store, along with a bunch of other outputs, which I'm not going to list here. So in the spec, instantiation is defined in terms of this auxiliary function, alloc module, which takes as an additional argument a list of values representing the initial values of the declared local variables in the module. And these values, in turn, have to be calculated by executing a series of initializer expressions, which are contained inside the module. However, these initializer expressions are actually allowed to reference state of the module, which is not allocated in S, but is allocated in S prime. So this is how the specification handles that. It just says that the initializer expressions execute in S prime. However, according to the formalism, you only get S prime by passing the result of this execution into alloc module. So you can see we have a circularity here, i.e. this definition isn't actually executable. So this causes some problems when we want to use the definition of instantiation in our verified interpreter. Because, as I said, this definition looks like it's kind of an executable function intuitively. But morally, what's really going on is it's more like an inductive predicate. But the spec kind of comes to our rescue here because it has this to say about what concrete implementations are expected to do. Because this definition isn't itself executable, but a real implementation has to implement this, so some other approach must be used. And the spec says this. This recursion is just a specification device. In practice, the initialization values can be determined beforehand by staging module allocations such that first, the module's own function instances are pre-allocated in the store, then the initializer expressions are evaluated, then the rest of the module instance is allocated. So in other words, the specification doesn't really describe the order in which things are expected to happen. The global initializer evaluation only depends on a subset of the effects of alloc module, and in real implementations, you carry out a bit of the alloc module abstract operation, then run global initializers, and then finish off the rest of the effects of alloc module, and this breaks the circularity. So we mechanize this approach as an executable function, prove it's equivalent to the inductive definition, and then this allows us to get an executable definition that we can use in the interpreter. So we're effectively verifying that the statement on the previous slide is correct. The specifications claim that this is equivalent to their non-executable definition. So the final part of our work is WASM-cert-coq, which is an entirely new coq model, a new mechanization of the 2019 W3C WASM semantics, written in coq. So this also includes an executable interpreter and type checker. And we replicate the proofs of the 2018 model, soundness of the type system and correctness of the executable interpreter and type checker. And we aim to use WASM-cert-coq to define a more ambitious verified interpreter, which doesn't share WASM-cert-Isabel's limitations regarding the unformalized definitions of numeric and parsing. And to work towards this, we've integrated with CompCert's integer and floating point libraries and the parseq combinator library to mechanize the concrete syntax of WebAssembly. So as a future goal, we aim to finish off the WASM-cert-coq interpreter and run it end-to-end on the test suite, and investigate how to make these interpreters more efficient so they can actually be used by industry potentially. And we'd love to hook into more coq developments which aren't available to WASM-cert-Isabel, such as CompCert-based verified compilation and some kind of Iris-based program logic potentially. And the final dimension we also have to consider is how are we going to keep these mechanizations up to pace with further changes to the spec? There are some pretty big extensions to WebAssembly in the pipeline. And it's an interesting question as to whether we're going to be able to continue to do the development work on the model to keep ourselves up to date with those. So that's everything I have to talk about. Thank you for listening, and please share any questions you have.
Thank you. If there are any questions, please put them in the chat. I was wondering, because I noticed indeed that you said, oh, then we had done all the efforts on formalizing things, and then then was a new version of WebAssembly, so everything was out of date again. Do you think there's any way to really make the formalization already a part of the process where the language is extended?
So it's already true that any extension to WebAssembly has to provide a pen and paper formalization. So in some sense, half the work is done for us. That's actually part of their standardization process, which is quite nice. So all we would have to do on top of that is to translate that into Isabel or coq. I say all, it's still quite a big amount of work, especially if we want to update the type soundness proofs as well. Yeah. In terms of whether the language standard would be interesting in making mechanization part of the process, I think they would see that as too much friction. We wouldn't want it to be the case that a feature is blocked just because no one's around to mechanize it. So I think until we're able to pay a lot of people to manage this as like a full-time job, that can't be part of the official process.
Okay, thanks. So that's not very hopeful in the end. But one other thing I was wondering about, so there have been other bytecodes that have been formalized both in Isabel and in coq. So and of course then WebAssembly has its own characteristics, but a lot of it is maybe also quite similar. So could you reuse those efforts in some way?
I wouldn't say that the efforts could be reused. It may, in theory, be possible to make some kind of generic theory development for a kind of a generic framework for a bytecode language, and then make, say, the JVM bytecode and WebAssembly instantiations of that framework. But I think just taking, say, an existing mechanization of JVM and trying to generalize it to also talk about WebAssembly would probably be more effort than doing a WebAssembly development from scratch, which is what we did.
And why do you think so?
Just because there are lots of, I mean, there are kind of unique things about WebAssembly, such as the way it does control flow, and the way it even just describes its global state. When we were making the WebAssembly mechanization, we wanted to be very careful to kind of follow exactly what the spec says in terms of its formal artifacts. And I think trying to do the minimum delta from an existing JVM development would lose that closeness to the text of the spec.
Yeah, okay, yes, that makes sense. Okay, thank you. I think with this, we have to wrap up and close this session. So if people are interested in talking, I would like to invite the audience and the speakers to come to Wonder Me for the break and have a nice coffee break there and have a chat with other participants. So I hope to see you all there. I will be there. Some of the other people involved in the organization of the conference will also be there. So please join up and have a chat with us. And we'll start, the next session will start in 20 past the hour. So we also hope to see you back there. Thanks for now.